Representing light clocks in velocity space. We begin with a single point in velocity space, which represents the velocity of an observer. Surrounding the observer in all directions is a light bubble with a radius equal to that of the speed of light. All of the light that this particular observer is capable of seeing is contained within the membrane of this light bubble in velocity space. If you're wondering why light takes the shape of a bubble in velocity space, think about what would happen to an instantaneous flash of light, exactly 1 second after the flash. At that moment, the light would occupy a bubble-shaped location in space with a radius of 299,792 kilometers in all directions from where the flash was emitted. This is not a coincidence. Speed is just distance divided by time, after all, but because special relativity says that the speed of light is fixed relative to the observer, and not relative to the source of the light, this necessarily means that the light bubble must be centered around the observer in velocity space, and not around the source of the light. As an observer, no matter where you are in velocity space, your light bubble must also move along with you in velocity space. The light bubble is represented here as a gray circle. This observer also has a light clock with them, and the observer is not moving relative to their light clock. The physical light clock, which includes two mirrors that are facing each other, also has a location in velocity space. The physical light clock itself is also located at this point at the center, where the observer is also in velocity space. However, the light inside of the light clock is bouncing between two mirrors and moving in the up and down direction. We can also attempt to represent where the light itself, the light which would make the light clock tick, would be located in velocity space. This light clock will be oriented in the vertical direction. When the light is moving in the upward direction from the mirror at the bottom to the mirror at the top, it will be found in the white dot directly above the observer. And while it's moving in the downward direction towards the bottom mirror, then it will be found in the white dot directly below the observer. This is what a light clock looks like when it's represented in velocity space, so long as the light clock is oriented in the vertical direction. Now let's add a second observer who has their own light clock. This second observer and their light clock will be moving at half the speed of light towards the right relative to the first observer. This also means that the first observer is moving at half the speed of light towards the left relative to the second observer. The second observer also has their own light clock, which is oriented in the vertical direction. But now that we have two light bubbles and two light clocks, we also have light in places where it shouldn't be, because the light that is bouncing around inside both of these light clocks is found in locations in velocity space which are outside of at least one of the two observers' own light bubbles. To fix this problem, Einstein proposed time dilation, which effectively means that the light bubble of an observer can shrink in velocity space, relative to the light bubble of an observer who is in a different location in velocity space. If time for one observer slows down relative to time for a second observer, then velocity space for them would also contract relative to the velocity space of a different observer. The light bubble of the time-dilated observer is shown in green. As you can see, time dilation allows the light bubble to shrink by just the right amount, such that the light of both light clocks is located in the light bubble of both observers at the same time. So far, it looks as though time dilation has solved the problem because we no longer have a contradiction. Because the two observers and light clocks are moving relative to one another at half the speed of light, the degree of time dilation, according to special relativity, should be equal to the square root of 3 divided by 2. This number can easily be derived with the help of some simple diagrams and Pythagorean theorem. This means that the radius of the green light bubble will be roughly 86.6% of the size of the radius of the gray light bubble. If these observers had been moving apart from one another at 75% of the speed of light, then this is how everything would look in velocity space. The diameter of the green light bubble would then be about 75.6% of the diameter of the gray light bubble. And if the observers had been moving apart at 90% of the speed of light, then this is how everything would look in velocity space. The diameter of the green light bubble would then be about 43.6% of the diameter of the gray light bubble. As the relative velocity between the observers approaches the speed of light, the size of the green light bubble will approach a single point with a diameter of 0, which would correspond to infinite time dilation. Now let's reduce the speed back to half the speed of light once more. As I said before, it looks like time dilation has managed to solve the contradiction that we started out with. But unfortunately, we still do require 2 light bubbles for 2 observers, which means that we need a total of 4 light bubbles. Ideally, we would only have 1 light bubble for each observer. From each observer's perspective, their light bubble is the larger gray light bubble, and the light bubble of the other observer is the smaller green light bubble. There is still a contradiction that remains. Both observers cannot be correct about whose light bubble is larger, or about whose time is relatively dilated. This contradiction leads eventually to the twin paradox, which is an attempt to sort out which of the 2 observers really has the larger gray light bubble, and which of them really has the smaller green light bubble. The standard interpretation of special relativity says that one observer is really stationary and that the other is really moving, and so the observer that is stationary has the gray light bubble, and the observer that is moving will have the green light bubble. However, we don't need to explore the twin paradox because I have an idea for how to modify the light clock thought experiment instead. Now let's imagine that instead of 1 light clock, each observer has 2 light clocks, and each light clock will contain a different color of laser beam. There is now a red beam and a green beam. These 2 light clocks are also oriented at different angles. The red light clock is vertical, but the green light clock is oriented at a 45-degree angle away from vertical. So let's add a second observer who also has the 2 light clocks, and just as before, the second observer is moving at half of the speed of light towards the right relative to the first observer. Just as before, we can add shrunken light bubbles to represent the time dilation of a moving observer relative to the stationary frame. For the red beam, because it's vertical and perpendicular to the direction of motion, we can add red light bubbles which are 86.6% as large as the gray light bubbles. This time dilation only works for the vertical light clocks, however. For the light clocks that are oriented at 45 degrees, the analysis will be significantly more complicated. For a light clock that appears to be moving towards the right, as the red beam is moving from the bottom mirror to the top mirror, it will appear to travel further and take longer. This means that it will take the light 171.8% as long from the perspective of the stationary observer. The radius of the green light bubble would therefore be only 58.2% of the radius of the gray light bubble. Meanwhile, on the return trip, the light would appear to travel a shorter distance and take less time. The light would therefore appear to take only 77.4% of the time and travel only 77.4% of the distance. This would mean that there would be a time contraction, and the corresponding light bubble would need to be significantly larger. This radius of the green light bubble would therefore be 129.2% of that of the gray light bubble. In this case, time dilation will not work to resolve the discrepancies that we see. If we attempt to use time dilation to resolve these discrepancies in this case, then we will end up with 8 different light bubbles. What we have now is a total mess. This is a big pile of contradictions. The more differently oriented light clocks we consider at once, the more contradictions and complications we will have. If the supervelocity and selection theory is correct, then there's no need to try to make these different observations make sense, because the light is actually everywhere in velocity space in latent form, and the manifest light that each observer sees is not really the same latent light that the other observer sees, because each observer sees light that is actually in a different location in velocity space. In case you're wondering how special relativity actually attempts to resolve this problem, instead of considering the velocity of the light in both directions separately, what it does instead is consider only the average between the two, which in this case would be a time dilation of 124.6%. And it is further hypothesized that the distance between the mirrors would decrease slightly due to length contraction from the stationary frame, and so the time dilation effect would really only be 115.47%. But the big question is, does it really make sense to average the two trips together such that only the round trip as a whole is considered in the analysis? This is equivalent to asserting that the one-way speed of light is not merely immeasurable, but also meaningless. I say that while it may be impossible to measure the one-way speed of light, it cannot be regarded as meaningless, and it cannot be ignored. If the one-way speed of light were meaningless, then the average two-way speed of light would also be meaningless. According to the supervelocity and selection theory of light, the speed of light is not meaningless. It is just far more complicated than it appears to be at first glance, because it's not really a single speed, but a range of speeds. The speed of light is a superposition in velocity space.